Hi everybody, this is Gigi from Kauai Community College. In this video, we will be talking about compound statements and how to build truth tables for compound statements. And then in later video, we are going to use truth tables to see if statements are equivalent, meaning they're logically the same. And then we're also going to use truth table to evaluate arguments. But for now, it's just an introduction, and we're just going to learn how to build a truth table. Okay, so let's get started. All right, truth tables. Okay, let's consider this statement here. Or better yet, suppose your friend came to you and said, Quentin bought pork rinds and he paid with a $10 bill. Okay, suppose your friend said that to you. Now, I want you to determine if he's lying or not, based on the information that I'm telling you. All right, so suppose scenario one, I came to you and said, Quentin bought pork rinds and he paid with $10 bill. You would say, oh, friend, you're so good. You're just telling me the truth, right? So that statement is true. Now, suppose I come and tell you that I was there with Quentin. He bought pork rinds, but he did not pay with a $10 bill. What do you say about your friend? Was he lying? Yep, that statement is false. Okay, scenario number three. Suppose I came to you and said, Quentin didn't buy pork rinds, but he did pay with a $10 bill. What do you say the original statement was? True or false? It is false. Okay, number four. This is the scenario where Quentin did not buy pork rinds and he didn't pay with a $10 bill. It is definitely false. Okay, so as you can see here, those are all the possibilities that could happen in terms of the truth of this statement. And we can see that when we have an and statement, it is only true when both parts are true. Okay, what we'll do in symbolic logic is we would compile this information in a table, and we call that a truth table. Okay, now we see here that there are two simple statements. P is Quentin bought pork rinds. Q is he paid with a $10 bill. So we can organize this information in a table like this, right? So scenario one would be true, true. Part P is true and Q is also true. Scenario two is you have true for P, but Q is false. Okay, and remember, a simple statement can only be true or false, right? So you have two choices for each one of those simple statements. Altogether, we have four combinations. So false, true, or the last combination would be false, false. And that's it. That are all your possibilities. So let's consider the statement P and Q, the truth value for that compound statement. Okay, so the and statement is only true when both are true. So the first scenario is true. And then we have false, false in the last scenario where both of them are false. Then the compound statement and is definitely false. Okay, that's the truth table for an and statement. Okay, what if we change that to an or statement? How is that different? Okay, so if I say to you, I'll bring my lunch or eat at Taco Bell. According to these scenarios, What do you think about my statement? 1, I bought lunch and ate at Taco Bell. Is this statement true? Yes, it's true. And I'm a pig. I ate 2 lunches. Okay. Now, scenario number 2. I brought lunch and I did not eat at Taco Bell. Is my statement still true? Yes, it is. Because it said, I will eat lunch or eat at Taco. I will bring lunch or eat at Taco Bell. Scenario number 3. I didn't bring lunch, but I did eat at Taco Bell. So I'm still telling the truth. Scenario number 4. I didn't bring lunch and I didn't eat Taco Bell. The statement that I said is false. I was too busy teaching classes, didn't eat lunch, didn't eat at Taco Bell either. That happens a lot. So in an overstatement, it is true when either or both parts are true. And in English, that's what we call that an inclusive or, right? So in symbolic logic, the word or is an inclusive or, meaning this or that or both. And so how do we organize this in a truth table? Suppose we have 2 simple statements, P and Q. Then we will have 4 choices as we have seen before. True, 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 false, false, true, or false, false. Those are all possible scenarios. Then the statement P or Q would be true when either or both are true. So we would have true, 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 and then false. And that's the truth table for or. Now remember the connectives in symbolic logic. We have and, or, and then what's next? If then. Okay, so consider this statement. If I take my car to Royce, then he'll fix my transmission. Okay, so again, these are the scenarios, and you think about it and see if it's true or false. I took my car to Royce, and he fixed my transmission. Yes, I am telling the truth. Scenario number 2, I took my car to Royce, but he didn't fix my transmission. Then this statement is false. Okay, so scenario number 3. I didn't take my car to Royce, but he did fix my transmission. What do you think? Was I lying when I said if I take my car to Royce, then he'll fix my transmission? I am still holding that truth in my statement because I didn't say anything about what if I didn't take my car to Royce, right? So this is kind of hard to digest, but the statement said, if I take my car to Royce. So when determining the truth value, we can only tell when I did take my car to Royce, okay? When I didn't, this statement still holds its truth value. So scenario number 4, I didn't take my car to Royce and he didn't fix my transmission. But since this is an if-then statement, the compound statement is still true. So to remember the truth table for this, we would say an if-then statement is false only when the if part is false, but the then part I mean, if the if part is true, but then the then part is false, okay? The first part, if, is true, but the then part is false, then the if then statement is false. Otherwise, it's true. So here we have P and Q. So we say true, 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 false, false, true, or false, false. If true, then the compound statement, if P then Q, is true. If true, then false, then the compound statement is false. If false, then it doesn't matter what follows, it is always true. And that's the truth table for if-then statement. What if you have a statement, if and only if? Okay, so remember, we have 4 connectives, right? Actually 5. The negation, which is the opposite truth value. And then we have the compound statement connectives that would be and, or, if, then, or if and only if. Okay, so if and only if means it goes both directions. Okay, so suppose you have 2 statements, P and Q. Then you want to take a look at P, then Q. P implies Q, or if P, then Q. And then you want to consider the other way around, if Q, then P. And then we take a look at both of them. Because if and only if means it goes both directions. Okay, so let's put the truth values up here. True, 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 false, false, true, and then true, false, false. Okay, so learning from the last truth table, if true, then the statement is true. If true, then false, then the statement is false. If false, then true, then the statement is true. If false, then the statement is true. Okay, now we're gonna go the opposite direction. So we'll go in from here to there instead. Okay. Okay, so if P, then Q. If Q, then P. If Q, then P. So true, true is true. False, true is true. True, false. If true, then false, then the statement is false. If false, then false, the statement is true. Okay. So we have considered both directions. The statement if and only if is the one with a double arrow, meaning we want to say and between these 2 combination. Okay. So when you have an and statement, it is true only when both are true. So the truth values for the if and only if statement is true, false, false, and then true. Okay, now this is something that you don't necessarily have to remember. You just need to know the if then truth table. And then you just figure out this one, make sure you think about both directions, okay? All right, so that would give you all the truth tables for us to be used for many other compound statements. Okay, so let's see if we can build a truth table for a statement that looks like this. Okay, so let's pay attention to the order of logical connectives, like the order of operations, right? So I see here that I have two simple statements, P and Q, right? Now, order of logical connectives said I'm going to go inside parentheses first. So then the next thing I'm going to consider is P and Q. And then once I have done that, I'm going to go out and say not Q would be my next order, because not negation is before or. And then the last thing I would consider is the whole entire statement, P and Q, or not Q. So that would be the order in which I will build my truth table. Okay. Now, let's put up our possibilities. True, 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 false, false, true, and then false, false. Yeah? Okay, an and statement is true when both are true. So this would be true, false, false, and then false. Okay. Not Q. That means the opposite truth value of Q. So we would look at the second column here and do the opposite truth value. So it would be false, true, false, true. Now we are looking at the previous two columns, and the logic connective is or. Okay, so remember that would be an inclusive or, either or both. So true or false is true. False or true is true. False or false, we would say that is false. False or true is true. And that's it. And that's how you built a truth table for a compound statement. Okay, it's not too exciting right now. We're just learning how to build a truth table. But when we actually use it to do things like determine whether two statements have the same meaning, or if an argument is valid or not. Okay, so that's coming next. And that's it for today.